Syzygy, episode 24, Black Holes Feeding on Colliding Galaxies. And welcome back for Syzygy, episode 24. Emily, sitting across the table from me on the microphone. How you doing?
Hello.
Welcome
Yes,
back.
I'm brilliant.
Good. You're over your lurgy.
Yeah, I sound way worse than I... No, hang on, I'll get that right.
Sound better than you were?
I feel way better than I sound.
Good. Emily's not been well. She's had a bit of a lurgy. She's been a bit green, but she's back. She's vertical, which is better than when you were a couple of weeks ago, a couple of days ago.
Definitely.
Ah, dear. So today we're talking about big things colliding. Galaxies in collision, which is pretty awesome stuff. And of course, as we talked about before on this podcast, down in the middle of galaxies lurks a supermassive black hole, typically. And so when you have galaxies in collision, then the supermassive black holes can collide as well, which is pretty exciting stuff in the world of astronomy. So, Emily, how are we going to start to unpack this? Where do we start this? First of all, what's the story?
What's the news? Well, the news is that, and this comes from Costatal, who did who published this work in the November 7th issue of Nature. And they published some really, really nice results from a whole bunch of different telescopes that they were using. And the bottom line, I think, of their research is that these black holes that are in these galaxy mergers, supermassive black holes from the centers of these galaxies, are actually growing a lot faster than we thought they were in the very late stages of their merger.
Okay. So why? What's going on?
So we got two objects which are in kind of collision. And it sounds like galaxies colliding should be kind of a very, very rare event, right?
It does. I mean, yeah. You know, when we look up at the sky, we see our galaxy. That's the Milky Way. All of the stars that we see in the sky are in our galaxy. And, you know, you're not seeing other galaxies just whipping through and bashing into stuff all the time in our galaxy. But turns out a bit more common.
Very, very common. And I think one way to imagine why that's the case is actually to think about its scale a little bit here.
Okay.
So I have a really great analogy. I like to use an orange.
Right.
It's not just because of the vitamin C content.
Hang on. Have you used an orange for an analogy before? Have
Yeah.
you pulled out the analogy orange before?
I love orange analogies.
Okay. All right.
Okay.
So Emily's orange analogy du jour. Let's go.
So if we imagine that the sun is an orange,
Yep.
let's just think about where our nearest star would be.
All right.
Do you want to have we done this guessing game before?
I think we have, and I should have paid more attention.
And you've forgotten. So let's do it again.
Say a mile away?
4,000 kilometers.
What? Oh, I have a feeling I did this last time as well, because I'm imagining it. And a mile's like a really long way, but 4,000 kilometers away.
To our nearest star.
That's like putting this in Australian terms, because I'm an Australian. That's Sydney to Perth. That's a really long way. An orange in Sydney and a grapefruit in Perth.
Yep. And you've also got, well, if you want in the Northern Hemisphere, we can do York to the North Pole.
Oh, so you've got like an orange in York and like a lime at the North Pole.
Yep.
Because spreading it around the citrus family, I think that's only fair.
Yeah, so it's fair, yep.
Good Lord. That's nuts.
So that's a really long way away. So
Yep.
the chances of two stars hitting each other in a galaxy, almost zero, right?
Okay, so I see where you're going with this. So even though, like if you look at a picture of a galaxy, right, one of these classic Hubble-style pictures of a galaxy, they're beautiful and they look like they're absolutely chock full of stars. Or even if you see a picture of the night sky on a really clear night where all of the stars, all of them are visible, it looks quite crowded. But in fact, the stars are very, very, very far apart. There's a lot of space. A galaxy is mostly space.
Yes.
Yep. Okay.
So stars, even if you smash two galaxies together, you've got all the stars, but there's lots of empty space in between them. But let's think about the smashing bit of the galaxies.
Okay.
So if our galaxy is the size of an orange, where do you think the next galaxy is?
Okay. Okay. I remember because we did this one before and I was paying attention. I just don't remember the answer. I'm going to say again, a mile away.
So not even the closest galaxy. So we've got some little galaxies in between, but our biggest neighbor, Andromeda Galaxy, in this scenario is 2 meters away from us.
I am so bad at this game.
You're really bad at this
I
game.
should stop using a mile.
It's
be
also
because I
not a
grew up-
metric unit,
Well,
Chris.
it could be because I grew up in the metric system, and I still haven't figured out what a mile is. A mile is anything from across the room to the other side of the world, give or take, as far as I'm concerned. So, what did you say? A couple of meters?
Yep, 2 meters.
Right. So you've got our galaxy. Wow, that's really close.
Really close.
Okay. And so I'm assuming then that that's not an absolute coincidence, that on that scale of orange-sized galaxies, you do tend to have galaxies quite close to each other.
Yeah, and galaxies are colliding.
So the idea of looking up into the night sky and seeing, like, beyond our galaxy and looking out to see the countless billions of galaxies that are out there in the universe, it's not so surprising that given that they are actually quite closely packed together, that you would see a lot of them colliding with each other. That makes sense.
Yeah, it's not like an even distribution. About half of all galaxies are kind of in these groups. And we did an episode about this, about kind of the large scale structure. And about half of them are in these kind of quite closely associated groups, like our local group.
Wow.
For us and Andromeda and
That's a
other
really
friends.
high percentage.
Really high,
That
yeah.
kind of reminds me a little bit of how surprising it was when you told me that it's actually really common to have stars in binary or multiple systems. So that's really common.
Very, very common. More than half.
More than half.
In our galaxy.
And now here
yeah.
we've got, roughly half of the galaxies that we see in some form of collision, some stage of collision.
Yeah. Gravity
Wow.
is a wonderful thing.
It is. It is an amazing thing.
So that gives us some ideas that actually these galaxy collisions happen all the time.
Okay, so this isn't rare. It happens.
Yeah. I mean, it doesn't happen overnight, is the other point that we're going to have to keep reminding ourselves of during this episode. So when we talk about things like the supermassive black holes are growing faster than we thought they were, I mean, we're talking about timescales of 10 to 20 million years.
So when we use the word collision in this context, it's really important to move it a little bit away from what we in our human-sized world tend to think of as a collision, right? You think of a car crash as being a collision where one object hits another object, bang, and it's over. Whereas on astronomical scales, the sizes, the energies, the timescales are incredibly different.
Yeah, so a whole merger process of two galaxies will probably take about 1 billion years.
And that, from an astronomical point of view, is still considered to be a collision.
Yeah, well...
Because in physics, I mean, it's something that you sort of learn. I think some students learn it in high school, and then you learn it as an undergraduate. That in physics, a collision is really just something where you've got something or a couple of objects coming into an interaction, interacting, and then leaving again, or sticking together and carrying on as a combined thing. But you've got before the interaction, and then after the interaction. And that interaction can be really, really quick, like, two particles colliding, which is incredibly quick. It's a tiny fraction of a second. It can be somewhat longer, but still very fast in our time frame, which is two cars colliding, which happens in, a second-ish. Or it can be much, much longer. So, for example, when a spacecraft does a flyby of a planet and does a slingshot around that planet to pick up some speed or to gain some momentum, that's a collision. And you can analyze that as a collision, even though it happens over days and weeks.
Yeah, I mean, the most basic definition of what we can say is that there's an exchange of energy.
Right.
And it's usually that the energy from the forward motion of at least one object is translated into some kind of friction or transfer of change in orbit, for example, in the case of the satellites. And then, it's changed that system because of that interaction. So in the case of two galaxies, collision, I mean, is a good term because you're looking at the ensemble of the whole galaxy, all the stars, all the gas, all the dust, all the things that make up that galaxy. But it's not kind of necessarily two galaxies smashing together, all the stars hitting each other and things, working like billiard balls in space.
No, it's not. I mean, you tend to sort of have this image of, stars bashing into each other and all hell breaking loose. And if you look at it, I mean, there's some amazing simulations of galaxy collisions out there. We'll put a link to some of these in the show notes. They're absolutely beautiful, and you can see these things swirling together and suddenly flying apart. But of course, none of the stars got even close to each other in the vast majority of cases. But you're dealing with such big objects with such a huge amount of of collective gravity all pulling on each other that it disrupts the thing itself. It's quite amazing.
It's really amazing. And what's really cool is that although the stars themselves are sort of, I mean, they're kind of unaffected, each individual star. So let's take just the example of a star in one of these galaxies that might be a bit like the sun, even if it's got a system of planets around it. It's kind of unchanged from this whole interaction, apart from maybe its orbit has been around the center, or whatever's going to be the new center of this galaxy is a bit changed. But the actual star isn't changed, really. But what does happen when these two galaxies collide is the other stuff that's not stars starts to interact. So particularly the gas and dust. And what's beautiful, and you can see in things like Hubble images when you look at interacting galaxies, is that gas and dust gets pulled around in beautiful ways. You get things called bridges or streams of material. And even in those streams, that gas and dust is changed by the fact that it's got gravity tugging it in all sorts of weird and wonderful directions. So often in a cloud, if you have a cloud of gas and dust, if you want to sort of trigger it into collapsing down and forming a star, you have to put a shockwave through it. In a normal galaxy, that might be something like a supernova explosion.
Yeah, we talked about that a couple of podcasts ago.
But in these in these mergers, it can be just the gravitational interaction of the merger itself can trigger shockwaves through this material, and actually you get a starburst where new stars are suddenly being formed because the gas is being pushed around, it's being pushed into collapsing down and forming brand new stars.
Can you work that one backwards and identify, you know, in a galaxy that you're looking at in the sky, can you identify that, hang on, there's this strange pattern within the galaxy where suddenly there's a whole bunch of new stuff happening and new stars turning on? I reckon there must have been a collision there. There must have been, or that must be in the process of colliding.
Yeah, definitely. And you can even sort of look back and say, well, there are kind of fossil streams of material in galaxies that probably happened because of some past interaction. We have one example in our own galaxy where we were interacting with two of our little dwarf neighbours, the Large and Small Magellanic Clouds, and that's causing a Magellanic stream of material, which has also got new stars which have been formed when that interaction was happening.
Is that still happening now, or
it's still going on? Yeah. So wow. We're very, very slowly eating those two galaxies.
Oh, poor things.
But it's slow. They've got a lot of warning.
Yes, I guess, you know, if they're still hanging around, it's, you know, it's their fault, really, isn't it, at this point?
So in the case of this study, what they're able to do, which is really cool, is to use some observations from different wavelengths of the electromagnetic spectrum. So we have lots of beautiful photos from Hubble of interacting galaxies. But if we want to look at what's happening now at the centers of those galaxies, what's happening to the supermassive black holes at the centers of those galaxies, then actually that's a real challenge.
Because as we've discussed before, supermassive black holes, amazing things, you know, ludicrous amounts of material has gone into building these things. And yet they are still really quite small and quite hidden from us, from the fact that they are in the centers of the galaxies, so they're fairly hidden anyway, and they're black holes, so we can't see them.
Exactly. So not a lot to go and kind of to use, especially in the visual part. And that's also because when you have these interactions of the two, and if these two supermassive black holes from the two galaxies are starting to come close, then they're shielded by a huge amount of material from these galaxies, the gas and the dust, and even the very high density cores of these galaxies where lots of stars happen to be. This just kind of like it blocks the center of our own Milky Way from us. Imagine doing that kind of 2 times over, and then with all this other material in the way as well.
Yeah, in a completely different galaxy, a long way away.
Exactly.
Yeah, this is hard stuff.
Yeah.
This is very difficult stuff.
Really hard.
Just going to take a guess before we go on to a little bit more of the details of colliding black holes and colliding galaxies, which is awesome. But I would assume that in a large number of cases, like we said a while ago, roughly, let's say 50% of galaxies are in the process of collision. That's, you know, in some way, or have collided or something like that. Was that right? Did I get that right?
They're in groups, so
in
they're
groups.
sort of gravitationally
Okay.
discussing matters with other galaxies.
All right, okay. I would have guessed that in the majority of cases, the galaxies are colliding in a sort of, you know, glancing kind of way, that the centers of those galaxies aren't on a direct collision course. And that a supermassive black hole in one and a supermassive black hole in the other, they sound really big, they're actually really small, and they'll tend to miss each other by quite a long way, but the galaxies are still colliding. But in a small number of cases, you would get that the black holes actually manage to get quite close to each other.
Yeah, and it all actually depends on your speed and your speed relative to the other galaxy. So if you've got galaxy 1 moving along in one direction and it passes by galaxy 2 that's moving along in the opposite direction, this is where the energy transfer comes from. And it's the energy of the forward motion that's transferred via gravity into this kind of frictional energy, which slows down both galaxies. So the whole process of interacting slows them down. And the question is, does it slow them down enough so that they just basically start to interact directly with each other and they form this merger? Or is it kind of like a glancing blow, as you say, and they kind of, this stuff material pulled out of the galaxy? It's the streams and the bridges that we tend to see in these wonderful images.
I can imagine if they're going really fast relative to each other, then a collision would basically just tear them apart. It might leave, something behind in the middle, but then you'd end up with this quite long, stretched out, whatever's left over after that collision. But if they're not going quite so fast, then that relative motion would swirl them together into something much larger and very interesting.
Yeah, and there's a wonderful example of this, actually. It's called Stephan's Quintet.
Ooh.
And it's a beautiful set of galaxies. So it's a quintet, although actually only 4 of them are interacting. The 5th one's kind of a background galaxy. But you can
Stephan didn't know that.
Yeah,
at the
Stephan
time,
didn't know that.
He's okay.
But you can see the bridges of material as all 4 of these things are kind of dynamically interacting with one another. And it's a beautiful, beautiful image.
All right, so we said that it's very difficult to see these supermassive black holes at the center of any galaxy, let alone, a couple of them merging together optically, because there's just so much stuff in the way. There's all of this gas, all of the dust, all of the stuff swirling around. Can't see them in that way, but they are nevertheless incredibly energetic things. So we must be able to see them in other ways.
Yeah, and it turns out that these guys are even super energetic because these are special types of supermassive black holes. They are feeding black holes.
Oh, feeding black holes. So stuff's falling down into them.
Yeah, because we stripped down a lot of this gas and dust and so on out of the galaxies. Now, if that wanders too close to the supermassive black hole, it's going to form a disk, and that accretion disk starts to glow, and then you get the black hole feeding from that disk, and a huge amount of energetic light is being put out. And that's what we can see, particularly in X-rays.
Yeah, it's an interesting phenomenon. It's easy to imagine stuff falling down into a black hole and, of course, never being seen again. That's the whole point of a black hole. But as material is falling down towards a black hole, and as it forms, as you say, this accretion disk, it's spinning around incredibly fast. It's orbiting around the black hole incredibly fast. Anytime you've got matter doing that, it's emitting a huge amount of energy, which can escape because it's still on the outside of the black hole. So the region around a black hole can be incredibly bright, and particularly in very high energy wavelengths like X-rays.
Yeah.
Right. So we can see them.
Yeah. So that's what I think was really clever about this study. They went and looked for systems of interacting galaxies that did have a high number of X-rays as detected by the Swift Space Telescope. And started basically a list of, these are interacting galaxies that seem to have lots of X-rays, so their supermassive black holes might be feeding. Now, how can we possibly look at that?
So how do you?
So this is when we need to shift wavelengths again. So we've gone up all the way to the high energy to find out what the black holes are doing. We're going to go a little bit down now and go infrared.
Right, so infrared. So that's not far out of the visible.
No, just below. So this is kind of your thermal imaging cameras and that sort of thing. And it's actually doing a very similar job here. Infrared light is not hampered by the dust and gas nearly as much as the visible light that we see. So this is the kind of technique we use to look into the depths of our own galaxy. Therefore, of course, we're going to use it to look at the depths of other galaxies.
Sure, it makes sense. So you've used the very high energy X-ray side to actually identify where are these things. Once you've got them, okay, let's look in infrared now and actually see some detail.
Yeah, exactly. And there was two ways that these guys did it. They used Hubble. Hubble has a near-infrared camera and looked about 385 galaxies interacting with Hubble. And they also used a really nice observatory called Keck, which is a really large
Is that the one
telescope.
in Hawaii?
Yeah, big one.
The good thing about being an astronomer is you get to go to all sorts of exotic places to use the telescopes.
Yeah.
If you actually have to go there. I mean, I guess increasingly you can do these things remotely, but
Depends
surely
on
there's always an
yeah.
excuse to go.
It's usually a good
Yeah.
So Keck is one of the highest resolution ground-based infrared telescopes we have, because it uses some very clever systems to improve and basically remove the effects of the Earth's atmosphere. And it was with this increased resolution that we were able to kind of tear apart, if you like, the insides and really see what was going on in the centers of these merging galaxies.
What did they see?
So that this is where they were able to see that these black holes are going to be merging a lot faster than models were previously suggesting. So they are on a collision course, these two supermassive black holes, and the merger process, which we thought previously from simulations and so on might last a few 100 million years on that nature, is really only going to be down to a few tens of millions of years.
That's a significant change. Like, that's much faster. That's not a little bit. That's a lot.
It's a lot faster, which is very, very exciting because it means that there's a lot of systems out there that we might even be able to see more dynamic interactions of.
If these processes happen somewhat faster than the models suggested they would, you know, a couple of galaxies in collision, a couple of black holes in collision. Hey, we thought we had hundreds of millions of years that over that for that timescale to actually play out. Now it's actually considerably less than that. That means perhaps it's going to be happening considerably more often. And one of the really interesting things that's happened in the last couple of years is a whole new area of astronomy which has opened up, which is gravitational wave astronomy, right? A few years ago, all the headlines were about, hey, we've detected gravitational waves, like at last, finally, from the merging of two black holes in a galaxy a very, very, very long way away. When black holes merge, that's incredibly energetic. And that wobbles, that final merger wobbles space-time in a very Einsteinian way and sends out waves through space-time, which we can detect with incredibly sensitive instruments.
And if we think about what that discovery was, so this is the good old famous GW150914.
I was going to say that.
To.
I thought that you probably have more fun saying that than I would.
I like these telephone numbers.
Yeah. I'm really good on the big detail. You're good on the fine detail.
So that black hole merger, that was a merger between two what we call stellar mass black holes.
Right.
So, but each of those black holes was around, one was around 36 times the mass of the sun. The other one was about 29 times the mass of the sun.
So these aren't supermassive black holes.
These are just massive.
These are just
massive. Yeah. Okay, the sun's pretty big.
Bog
I'll give you
standard,
that. Yeah.
Common or garden variety black holes.
Yeah. Yep. So they're the kind that maybe have been left behind by a star exploding at the end of its life. So it has kind of a stellar-ish mass.
Yeah.
Those ones are still confusing. I'm not sure we still quite understand where they came from.
All right. Well, we'll leave that for another time.
The point is they're small.
Yeah.
Compared to these guys that we're talking about.
Which are millions,
if not billions of times the mass of our sun.
So when those merge, wow. That's going to be off the charts.
You think you got gravitational waves from just a stellar mass black hole merger. Imagine billions of stellar masses coming together in a black hole merger.
Now, of course, it's still tens of millions of years time scale. So it's not like we can go, let's just keep an eye on that galaxy there because in 5 million years' time it's going to happen. Like, we're not going to be doing that. But I guess the point is that not only can we see where these things are happening in galaxies that are out there in the sky, we can see things that are in the process of merging, and it seems to be happening faster. But that might imply that actually we've got a better chance of detecting these things happening because they may be happening faster and more often.
Yeah, I'm really not sure about this argument of more often, though.
I don't know. I'm plucking that one out of the air.
I know.
I'm hopeful.
I don't know. Does it work like that, though?
Does it work like that? Well,
in a nearly infinite universe.
Going to have to go and think about that one. Any
I think,
astrophysical statisticians want to get in touch with us?
Yeah. I think what's really interesting, though, is that it does help our models of galactic evolution.
Okay.
To understand where different types of galaxies come from and how fast you can form particular types of galaxies.
See, I was getting very excited about the, big explosions and we can detect them thing, whereas you're being very, very sensibly astronomer, which is, but no, this tells us about our models. Oh, okay, all right, fine, you win.
Yeah, but it's interesting to know how bad our models are.
Well, yeah, okay.
Okay, so we have lots of different types of galaxies in the universe around us. We have spirals like our own. We have these things called ellipticals, which are kind of just blobs of many, many stars. And all sorts of weird and wonderful things in between and other. And we don't really exactly understand if there's some evolutionary links between the different types of galaxies. Hubble gave it a good old crack in the 1930s. He was almost definitely wrong with how he decided that galaxies evolve. But the reason why that Hubble's work is still in astronomy textbooks today is because it turns out we don't really have a better concrete model at this time. We have some ideas of how some types of galaxies evolve into some other types of galaxies, but there's no general pattern yet.
It's a little bit like organizing all the birds you can see by, well, this bird looks a bit like that bird because they've got a similar kind of beak. You know, galaxies are still kind of categorized by, well, they're this kind of shape and they're a bit like these other ones, but it's what you're saying is it's not entirely clear how or even if galaxy evolution kind of goes from one end of a scale to another end of a scale and what's going on along the way.
Yeah, and the really hard bit is these galaxy mergers happen along the way. So it's not just you take one galaxy and wait and watch and see what happens. It's you take another galaxy and then it might interact with this type of galaxy and this will happen. Or maybe it did this, or maybe it was left all on its own and it did nothing.
Or, I mean, could it be that some of these strange galaxy types are actually what you get when you merge a couple of galaxies together and combine them and, that's what that is?
Almost certainly. So I think that helping us understand the zoo of galaxies that we do see out in the universe is actually really useful. And knowing the timescales of how things interact really does help that.
So having a better understanding of what's going on with some galaxies that you can observe, you can measure the timescale over which they are merging, over which the supergalactic black holes are coalescing together. And as you said a couple of podcasts ago, last time we were talking about supermassive black holes, that the black hole at the center of a galaxy has an enormous influence on the evolution of everything else in that galaxy. Tiny though it may be as a pinprick in the middle there, it's incredibly important in the evolution of that galaxy. So it kind of makes sense that if you can get some sense of what's happening down there in the center and during a merger, then that would help your overall model of what's going on generally.
Yeah. And one of the ways we might want to apply this model is actually in an example very, very close to home.
Ah, okay.
So
bringing it all back home.
Yeah, I'm gonna put this out here now. I'm afraid that the Milky Way's days are numbered.
What? Don't tell me that.
We are on a collision
course. What are you talking about?
With another galaxy, the Andromeda Galaxy.
Oh, what? We're going to collide with Andromeda?
We're going to smash basically straight into it.
Wow. Okay. How soon?
Well,
how much time have we got? Have I got time to get my affairs in order, as they say on the TV?
Yeah, probably, because it's going to take about 4 billion years until that really kicks off.
I'm feeling a bit better about that now. But wow, like a straight on bang, we're going to hit each other.
Yeah, and we've sort of known we were headed into the into the same region of space, shall we say, for quite a long time. We've measured that Andromeda is blue shifted, which means its light is coming towards us. So the whole galaxy is sort of moving towards us at an insane speed. It's moving towards us at 110 kilometers every second.
Okay, that does sound incredibly fast. Then again, it is a very long way away. So
it's
not something that we need to worry about now, but it's going to happen. It's going to happen a few billion years down the track.
Yeah, we weren't sure until quite recently whether we were going to get a glancing blow, whether we were going to miss each other entirely, or whether we were going to smash head on.
Hey, what are the relative sizes? Who's bigger?
Andromeda.
Really?
Just a bit.
Oh.
I think they're about 25% larger than we are.
Right. But it's still going to be a hell of a collision.
Oh,
if you could get a bit of distance from it and watch over the next several billion years, that would be really quite interesting.
It's going to be beautiful.
Wow.
And there's probably going to be a third galaxy jumping in on there as well.
Really?
Yeah, the triangulum.
Wow. So you said that we weren't sure whether or not it was actually going to hit like head on or if it was going to be a glancing blow. So when did we find that out? How do we know?
So we finally were able to make really precise measurements of is Andromeda shifting kind of left or right in 2012 with Hubble. And so it was only just very recently that we figured out, oh yeah, we're in trouble.
It's coming right
We're
at
in
us.
for a head on. Andromeda hasn't moved in all the time we've been observing it, at least to our detection limits. So pretty much it's going to smash straight into us.
That must have been a really strange realization to come to. It's like, okay, we can see, look, Andromeda, it's coming roughly in our direction. So is it going that way? Is it going that way? It doesn't seem to be doing either of those. Hang on, there's only one explanation for that. It's coming right at us. But really slowly, so there probably wouldn't have been a lot of panic in the voice there.
No.
So going back to what we were talking about earlier then, so there's a lot of space in galaxies. There's a lot of distance between stuff. Looking at it from a distance, you would see 2 or 3 galaxies colliding and just ripping each other apart. But if you were to see it from Earth, if we were still around, would we even notice?
Well, there have been lots of people trying to model this, what's going to happen to exactly the sun in this scenario. And of course, we don't have the exact precise locations and masses of every object in these two systems.
Why not? What have you been doing with your time? Come on.
Well, the Milky
Seriously.
Way has like 300 billion stars. Andromeda is maybe 400 billion.
Excuses. Just excuses.
That's
Seriously.
quite a few measurements that
All
we
right.
have to make.
Okay. But statistically, you could do it.
Yeah, I mean, we
say,
could look at...
given a star, roughly here, and a distribution of stars roughly like this, you could figure out roughly what would happen to roughly that star.
Yeah, probably what we'd do is we'd say, here's a million possible scenarios. What happens in the majority of those scenarios?
Yeah,
right?
let's play it out over and over and over and over and over again.
Yeah.
And what's likely to happen. So what is likely?
Probably not much.
Oh.
It seems to be the general consensus. We'll probably end up just merrily orbiting the centre of whatever is going to be in the centre. It's going to be a new galaxy. We've already got a name for this new galaxy.
Good. Tell me it's not a bunch of numbers.
No, it's called Milkdromeda.
Oh, nice.
Yeah.
Nice. In the grand tradition of Hollywood naming things, Sharknado, Milkdromeda. I like it.
So we'll still be orbiting some kind of central point in Milkdromeda. We're still going to have our solar system. That's very much gravitationally bound to our sun. There's not much that it can do to kick that off. We will have other problems, though, probably that we'll be worried about. Well, 4 billion years is kind of when the sun starts to run out of fuel.
Okay.
4 to 4.5, depending, exactly how much hydrogen's left over in the sun.
And when the sun runs out of fuel, what's it going to do?
Well, it's going to become a red giant. It's going to swallow up the Earth inside of it.
It's going to be that big.
It's going to be really big.
Wow.
So
we're going to have bigger problems at that point.
Yeah, we're probably not going to be interested in the merger of Milkdromeda at all.
That's a real shame because I would imagine like the night sky looks good enough now if you manage to get out of the city. And as we encourage everyone to do as often as we possibly can, you should do that. But in a couple of billion years, it's going to look really quite extraordinary as these two galaxies come together. 2 Milky Ways effectively across the sky in merger.
Yeah.
Wow.
So-
But we're not going to see it because we're going to be burnt to death by a giant star.
Yeah.
Yeah. That sucks. That's really bad timing. That's really bad timing.
It's really bad.
Who do I write to? Can I write to my local MP? That's not fair.
Well, you will get a beautiful view of Andromeda in the night sky in the few billion years leading up to this, right? At least in the last couple.
I mean, here it comes.
Yeah.
It gets slowly but surely
it's
getting
already
bigger and
really
bigger.
large, and actually, in terms of angular size in the sky.
It is, isn't it? It's like, if you look at the size of the moon, it's like 5 or 6 moons across. It's just really, really dim, so we don't tend to see it. But when you see it, when you figure out the size of that in the sky, it's huge.
Yeah. And so it's just going to get brighter and closer as time goes on. And I've seen some really nice...
Really slowly.
really slowly. And I've seen some really nice sort of people photoshopping, what the night sky is going to look like in 1.5 billion years' time or something like that, when Andromeda is just this big streak up through the night sky. It's really quite cool.
So we can kind of pretend that this is what it would look like, but we're not going to be around to see it.
We're definitely not. I'm not planning on it.
Such a shame. And that brings us once again to the end of an episode of Syzygy. Look, we always really enjoy doing these shows. And if you enjoy listening to these shows, then there's a whole bunch of ways that you can get in touch with us and a bunch of ways that you can help us out. So first of all, let's start ticking these ones off. You can talk to us on Twitter.
The Tweetyverse.
The Tweetyverse. What's our Twitter handle, Emily?
We are at SyzygyPod. That's an S and then a Y, then a Z, then a Y, then a G, then a Y.
Which gets you a lot of points in Scrabble. If you just... Here's a tip for new players. If you turn an N sideways, you get a Z, and then you can play it in Scrabble.
Don't
you can.
cheat.
Yeah. Look, if you go on Facebook and search for the Syzygy podcast, or just facebook.com/SyzygyPod will get you there as well, or just go to syzygy.fm. Go and find our webpage. You can find all of the past episodes on there, all of the show notes, the works, as well as a contact page. You can send us a little hello. If you've got any questions, something that you've always wanted to know in the world of astronomy, send us a question. We have done in the only 20-something episodes that we know. What are we on now? 24?
24.
We've already done 2 episodes based on listener feedback. So you can be number 3. That'd be fantastic. We'd love to hear from you. If you also want to get in touch with us or you want to help us out in doing what we do better, then there's a couple of ways you can do that. First of all, number 1, go and give us a review, because the more people who put reviews up on things like the Apple Podcasts page, give us a 5 stars and a little blurb about how great this show is, the more other people will find us, because it helps us to rise up through the infinite number of podcasts that are out there. So that's one thing that you can do. You can tell your friends and your family and say, hey, I've been listening to this thing. I think you'd enjoy it, and point them in our direction, syzygy.fm, and they can find all the details there. One last way is that you can go to our Patreon page, patreon.com/SyzygyPod. Go there and you can become a patron of the show. If you pledge $1, couple of dollars, $10 or pounds if you're here in the UK, then that would come to us every month and help us to do the things we do better than we do them. It gives us a chance to sort of grow and expand and do many more exciting things and put, high production values into the show, which is something that we always enjoy doing. What that really means is actually spending a bit more time doing it, ironing out all the bugs.
And a heartfelt thanks to those who have already signed up to be a patron of the show.
Exactly. I'd like to give a shout out to Russell Townsend and to Chris Baker, both of whom have pledged money towards the show through our Patreon page. So huge thank you to you guys. It's really quite humbling, actually, to know that people believe in the show enough to go, you know what, I really am going to do that.
Yeah, big Syzygy love.
Yeah, huge Syzygy, astronomical sized love, I think it's fair to say. But on that, I think it's time to wrap this one up. So we will catch you again next time in roughly a week's time for a bit more astronomical love on everyone's favourite astronomical podcast, Syzygy. Say goodbye, Emily.
See you later.
We'll catch you next time. Bye-bye.
I know so many words that would be great for Scrabble if it just had more letters in it.
Yeah, I mean, you'd get a lot of points for astrophotography. Syzygy alone, you could get about 400 points in the right place. All those Zs and Ys.
Are there that many Zs?
No. That's the problem.
So you'd have to cheat, basically, and bring your own Zs.
Turn N's on their side and you've got a Z, haven't you?
I'm never playing board games with you, Chris. Good times in the Christmas
Stuart
household.
Yeah, I usually end up with a beer doing a crossword or a jigsaw puzzle.
You're so
nerdy.
No.
What?
Metro.
What?
That's totally Metro, isn't it? I think it is. Yeah.
Really? What, doing a crossword and a jigsaw puzzle? How is that
beer? With a craft beer, I bet.
Oh, well, of course.
And you got a moustache, so,
I'm not entirely sure this is
and a check shirt. I'm just going to have to call you on this one, Chris.
Okay, all right. I'll take that. At least I'm not hipster.
Oh.
We need to finish this show, okay? A small subsection of this may be going at the end of the show.